In this unit, we're going to start looking at chemical reactions and how they happen and how they work. So first we need to talk a little bit about how we write them. So writing reactions is how we as chemists communicate what is happening at the molecular level. So there are a few sort of standard practices, some of which are relatively obvious, but just want to state all the important things to make sure we're all on the same page. So firstly, they're always written with what we call the reactants on the left and what we call the products on the right. So if we have some very generic reaction, A plus B forms C plus D, we would call whatever is to the left of the arrow my reactants. The reactants are the things that are used up in the reaction. RxN, if I haven't used that before, is a very common abbreviation for reactions, so you're going to be seeing that a lot in this unit. The things to the right of the arrow are my products that are created by the reaction. And the arrow in between shows the direction that the reaction proceeds, saying that we are taking A and B and we are turning them into C and D. So make sure you are using an arrow and not an equal sign. Equal sign doesn't have that directionality. We always use arrows in chemical reactions. So the other thing to be aware of that we talked a little bit about before is that chemical reactions must always be balanced. It's not really a valid, complete reaction until it is balanced. And what we mean by balanced is that there must be equal mass and charge of our particles on both sides. So we usually want to look for the same number of atoms of each element being present on both sides. Skip some words. Of atoms of each element on each side. So, and we should also have the same total charge on each side. So if you look at a chemical reaction that you are given and that is not the case, the way that we fix it or the way that we balance a chemical reaction is to adjust our coefficients. So we use a coefficient in front of a reactant or product formula to adjust the number of molecules of that species, of that compound, that are taking part in this reaction. So that are either consumed or produced in our reaction. So the one thing that folks are often tempted to do, but you should not, is you should not change the subscripts. So the subscripts in a chemical formula are an inherent part of that chemical's identity. H2O, that 2 is a subscript. The identity of a water molecule is that it has 2 hydrogen atoms for every 1 oxygen atom. If you change that subscript, if you're like, oh, well, I need 3 hydrogens, let's make it H3O, that's not water anymore. You've changed the identity of that chemical, and you don't want to do that. If you're given a reaction that says water reacts with something else, you need the water to stay water. So do not change your subscripts, because changing subscripts changes the identity of the chemical. So you're looking at a completely different reaction. We want to just change, maybe I need 2 water molecules in this reaction, that 2 waters react with one of whatever else it's reacting with. So we can change how many molecules there are, but we don't want to change the identity of the chemical. So let's, also one more thing to consider, sorry, before we look at examples. Also, at least for right now, we always want our coefficients to be integers. There are some instances when we can use fractions, but for now we're just going to stick to integers. And they should be expressed in lowest terms. So if you find that you need 2 reactants and 4 products, that's the same as 1 reactant and 2 product. A 1:2 or a 2:4 ratio are the same thing. So we want to express those in lowest terms. So now let's look at some examples. So first up, we are given this reaction where zinc is reacting with hydrochloric acid to form zinc 2 chloride and hydrogen gas. And we want to balance this reaction. I will tell you right now it is not balanced. What we want to do is count up how many atoms of each element do I have on each side. So on the left currently, I have 1 atom of zinc, I have 1 atom of hydrogen, and I have 1 atom of chlorine. On the right, I have 1 atom of zinc, I have 2 atoms of chlorine, remember that this subscript applies to the thing right before it, and I have, for the same reason, 2 atoms of hydrogen. So you will notice that we have a mismatch between the numbers of hydrogen and chlorine atoms on the left versus the right side of this equation. The zinc is fine as is, we don't need to adjust that. So looking at this reaction, trying to figure out how do I adjust this, I need to increase the number of hydrogen and chloride molecules, or atoms rather, hydrogen and chlorine atoms in the left side of the reaction, and I can do that by adjusting the coefficient that I put in front of the HCl. So I currently have 1 of each, I need 2 of each, so I am going to stick a coefficient of 2 in here, and that means I now have 2 of each of these. So coefficients are saying that I have 2 of this entire molecule. I have 2 molecules of HCl, so I have a grand total of 2 H's and 2 Cl's. So remember that this guy is applying to the entire molecule, all of the elements in it, in contrast to a subscript applies only to the one element immediately before it, not to everything in the compound. So let's look at another one. So this one is going to work out to be a little bit more complicated, but why don't you stop here, pause here, and try to take the same approach that we just did to the last reaction to see if you can balance this one. So we can start out by kind of taking inventory. After a while, you can probably start to skip this step, but at least when you're starting out, it helps a little bit to see exactly what it is that you need to adjust. So currently on the left side, I have 2 atoms of carbon, I have 4 atoms of hydrogen, and I have 2 atoms of oxygen. On the right side, I have 1 atom of carbon, I have 2 atoms of hydrogen, and I have a total of 3 atoms of oxygen. So, looking at this, we see that oxygen appears in a couple places on the product side, which is going to make that one kind of the trickiest to potentially balance. So I would leave that to last, since you have kind of multiple different options for how you end up balancing that one. This is a case where choices are bad. We want to know the right answer. So for instance, what I mean by that is we have 2 atoms of carbon on the left and only 1 atom of carbon on the right. Carbon only appears in one place. If I want on the product side, carbon only appears in one place on the product side. Sorry. If I want to make these 2 numbers equal, I have no other choice but to put a coefficient of 2 in front of the carbon dioxide. That's the only way that I can turn this to 2 atoms of carbon and make those numbers equal. Similarly, for the hydrogen, I have 2 hydrogen on the right, 4 hydrogen on the left. On the right side, on the product side, hydrogen only appears in water. So the only way that I can make this adjustment is by putting a coefficient of 2 in front of water. Now, by making those 2 previous adjustments, we have also changed the number of oxygens, sorry, apparently I'm a mess today, of oxygen atoms in the right side of our formula as well. I now have 2 times 2 for a total of 4 from here, plus 2 times 1 for a total of 6 overall. So at this point in my balancing process, I have ended up with 6 atoms of oxygen on the right side, which does not match the 2 atoms that I currently have on the left. So now, once I've done everything else, I have no other choice but to put a coefficient of 3 in front of that O2 on the left, and that gives me the grand total of 6 oxygen atoms that I'm looking for. So this reaction, when it is fully balanced, tells us that 1 molecule of ethene reacts with 3 molecules of oxygen gas to produce 2 molecules of carbon dioxide and 2 molecules of water.